Okay, let's get started and let's pick up where we left off in the previous lecture. Just as a kind reminder to what we did in the previous lecture, at the end of the previous lecture, we used the Bellman operator to have further and further approximations to the value function of the infinite case. So we saw that through the finite cases, when the time span uh, over which the agent is supposed to maximize, so if the time span is increasing and if it goes sufficiently large, we can find, in the end, we can find the limiting function as a limiting function, the value function of the infinite case. This was the so-called value function iteration, and this whole process is built on convergence. Convergence of functions, convergence of sequences, finite and infinite sequences. So in this lecture, we will look into the mathematical background that we need to be sure that we can converge, we can find the value function at the end of the convergence process. During this exercise, during that exercise at the end of the previous lecture, we took a number of things for granted. We didn't check if the space in which we were moving was appropriate. We didn't check if the operator, the Bellman operator we used, was appropriate to our purposes. We just took them for granted. It worked, okay, because it was an appropriately selected exercise. But when we need to build a new model, we cannot take it for granted that our operators uh, will be working. So we need to make sure that we can really converge to the value function. We need to make sure that we converge towards the optimal program consumption path or investment path and the like. So in this lecture, we are going to lay the mathematical foundations upon which we can build our theories and models. A convergence takes two things. Convergence is to be measured and convergence is to be ensured. By measurement, we mean that we move in a space of points, in which space points can be interpreted in various ways. So points can be the normal physical points of the three-dimension Euclidean space. Points can be finite or infinite sequences, and points can be functions. So okay, spaces contain points, but these points can be various things. And if we converge in a space, it means that there is a distance between the points, and we can measure this distance. To refer back to the example of the previous lecture, in which we use the Bellman operator to generate approximations in finite cases to the value function of the infinite case, these functions were points. In the points of functions, some functions, continuous, concave functions. So we had points in the space of continuous and concave functions. When we were converging towards the value function of the infinite problem, we had points in this space, and if we converged, and we did, it means that the distance between these consecutive points was decreasing. So we had a sequence of points, a sequence of functions, and the distance between any two consecutive functions was decreasing. This is convergence in the way we use the term in the case of convergence towards the value function of a problem. So we need to measure convergence, and to do so we need appropriate spaces. So we will define spaces in a way that distance between points could be measured. And number two, convergence is to be ensured. So we need to make sure that we use operators like the Bellman operator in the previous example. So we need to make sure that we use operators that have the hope of leading to the value function as a limiting point in the end. So we will, in this lecture, we will set up a number of conditions, circumstances, criteria which we need to abide by in order that we have appropriate spaces and appropriate operators. So this is what we are going to do today. But before doing so, I suggest we should build an intuitive and straightforward idea of the convergence of functions. We have this simple figure to build a simple and intuitive idea of the convergence of functions. We have a domain, which is a closed interval AB along the horizontal axis, over which we have a series of functions. The limiting function is represented by the red curve, and the green curves represent the series of functions through which we are converging towards the limiting function. Let's pick an arbitrary x from the domain. We can see that the series of the approximations, let's call them approximations, so we can see that the approximations, each of the approximations, have a value over this arbitrarily picked x, and these approximating functions generate a series along the real line, a series of numbers, real numbers, towards the value of the limiting function over this picked x point. So given that x was picked completely arbitrarily, we can do this to any point within the domain. So our understanding, our intuitive idea of the convergence of functions is something like this. So if functions converge towards a limiting function, it means that at any point in the domain, these functions generate a series of real numbers, and this series of real numbers is converging towards the appropriate point of the limiting function. So this intuitive idea suggests that the convergence of functions is to be understood as an analogy of the convergence of numbers, of convergence of series. So this is what we are going to do now. Okay, so how to understand the convergence of functions as an analogy of convergence of real numbers. So let's start with the basics. along the real line, it is quite easy to understand convergence. This is point X, and we are converging towards this point along the real line. You can see that convergence means getting closer and closer to this arbitrarily picked point. So the distances between the steps are simply decreasing. Okay, so this is convergence along the real line. In the case of simple two-dimension case, in the case of a simple two-dimension space, we have something really similar. Let's have a point here. This is the arbitrarily picked point X, which has two coordinates, x1 and x2. Let's pick a point X, which also has two coordinates, and let's say that this point is converging towards the limiting point. So along this convergence, we have further and further points, and this is gonna be x1, this is gonna be x3. Sorry, I'm confusing the indices. Okay, so we are converging to consecutive points to the limiting point. This convergence means that the coordinates, let me use the white, the coordinates are converging to the coordinates of the limiting point. So this is how convergence can be pictured, can be imagined in a simple two-dimension space. And we can go further because this space can be easily extended to a three-dimensional space. And convergence is going to mean the same. Nothing changes except for the number of dimensions. Okay, so we can do this up to any finite dimension. So, for instance, in this case, our points or elements in the three-dimensional Euclidean space. But we can interpret points in the L-dimension Euclidean space. And here, I think here, something interesting happens. So let's have a look at the coordinates. So this is the coordinates of a limiting point in the L-dimension Euclidean space. This is a vector. Normally we call it a vector, but it's also a sequence. It is a sequence. So when we are talking about the convergence of points in the finite dimension Euclidean space or finite dimensional version of the same Euclidean space, we are talking about the convergence of vectors, not just point vectors, and together with vectors we bring in the idea of finite sequences, because a vector is a finite sequence. So here we are. Here we go with the convergence of finite sequences. But what if we interpret a point as an infinite sequence? It takes nothing. We just drop the idea of having a finite vectors or finite sequences. We extend the space towards infinite sequences. And here comes the fun part. Let's have a function. Let's have a function. This is going to be really simple. This is a normal function over a domain. Okay. So we are defining the domain over which we have a function. The function, actually any function, defines an infinite sequence, because if we go along the curve, we are going through an infinite sequence. So if we have finite vectors, we have finite sequences which can be easily extended towards infinite sequences. And if we have infinite sequences, we have functions. So we can get from the real line, the simple real line, towards the convergence of functions through some easy steps. So in the end, we have the necessary vision, the necessary idea for understanding or visualizing the convergence of functions. Functions are for us are no more than infinite sequences, and infinite sequences, the convergence of infinite sequences, can be easily imagined as an extension, as a simple extension to the convergence of finite sequences vectors in the finite dimension Euclidean space. Okay, now that we have some simple ideas on convergence and distance between points and points in general, now we can turn to more fundamental questions. We have two questions. The first one is how to measure convergence. We have a simple answer. We need to make sure that we are iterating in an appropriate space, which means that it is supposed to be a space in which the distance between 2 points can be numerically expressed. Let's start with the basics. So we are starting from the concept of a real vector space. Please remember, a vector is a finite sequence. So we have a real vector space in which we have points which are vectors, and these vectors are subject to two operations, addition and scalar multiplication. To put it simply, a space is a real vector space where the sum of elements and the multiplication of any element with a real scalar remains in the space. So simply put, it is a real vector. A space is a real vector space if we have 2 points, any 2 points in the space, and if we add up these 2 points and we remains in the space, so we have a sum which is still in the space, and if we multiply a point vector with a real scalar, the result, which is the lengthening of the same vector, remains in the space. So this is a real vector space. In this space, in a real vector space, we cannot measure distance. Distance is defined because we can multiply, for instance, y with -1, and we can add up x minus y. So we can interpret the distance as the difference between 2 points, 2 vectors, but now we cannot measure the distance between the points. So we have the distance, but we cannot measure the distance. To this end, we need a metric or distance function in order to have a metric vector space. So if we have a metric, which is a distance function, now we have the distance between any 2 points, and now with the metric we can measure the distance between the points. Another related concept is the norm. The norm is another measure of the length of vectors. So just try to go back to the simplest two-dimension case. If we have a two-dimension space and if we have a point in this space, this point is a vector. This point defines a vector from the origin to the point. So we have a vector. If we have a point, we have a vector. And with the norm, we can measure the length of this vector, which is interpreted as the distance of the point from the origin. So this is the reason why I told that the metric and the norm are related concepts. Because instead of measuring the distance between points, we can measure the length of the difference. Again, please go to the paper and pencil and try to pick 2 points in a two-dimensional space. If you have 2 points, you have 2 vectors, and if you have 2 vectors, you can have the distance, you can have the difference between these 2 points, and instead of measuring the difference between these 2 points, you can measure the length of the difference between the points, which is also a vector. So we can use the norm as a metric. We can use the norm to measure distances between points. I mentioned the other day that exercises are instrumental to completing the book. So please pay special attention to exercise 3.4a and f, because these exercises prove that the set of continuous functions on any real domain with the subnorm is a normed vector space. So we have some results. We can use norms at metrics. So we can use any norm to measure the distances between points, and as a result, we can measure the distance between points. So now we have the conceptual tool to measure the convergence of processes. So please remember, we defined the convergence, any convergence of points, as a process during which the distance between any 2 consecutive points is decreasing. Now we have the norm and we have the metric as devices to measure the distance between the points, and this is an achievement. The usual question sounds like this: is a series of series or a series of functions convergent? To answer this question, a proper definition of convergence and a proper criterion is needed. Let's start with the definition of convergence. You can read the definition in the slide. it comes directly from our textbook, the Lucas-Stokey book. So let's try to interpret it. We have a sequence, and we want to judge if the sequence is convergent or not. We can say that the sequence is converging towards a limiting point in the space if we can go arbitrarily close to this limiting point. So as the epsilon, which is an upper bound on the distance between an element of the sequence and the limiting point. So this epsilon, this upper bound, can be arbitrarily small. It can approach to zero, even zero. Then this sequence is convergent. This is a very simple idea. So please remember what we were talking about a couple of minutes ago when we were trying to catch convergence along the real line at the blackboard a couple of minutes ago. We were going closer and closer to the limiting point. This is what convergence means, getting closer and closer to a limiting point. This is a very simple idea, but it is quite difficult to apply in practice, because if we want to say if a series is convergent or not, we need the distance. We need to measure the distance between the limiting point and the elements of the sequence. Okay, we can do this because we are moving in a metric space or in a normed space, so we have the devices by which we can measure the distance between the elements of the sequence and the limiting point. The problem regards the limiting point. So if we want to use this definition of convergence, this simple definition of convergence, we need to know the limiting point. So if we know the limiting point, then we can measure the distance between the elements of the sequence and the limiting point. And if we experience that the distance between the elements and the limiting point is decreasing, then we can say that the series is convergent. It sounds easy. It sounds easy, but it cannot be done in practice because sometimes we simply don't know the limiting point. So we needed another criterion, and this is the Cauchy criterion, and this is very useful. Actually, this is a brilliant achievement because the Cauchy criterion is built on the inherent or inner features, qualities of a sequence. So we can, by the Cauchy criterion, we can judge the convergence of any series without knowing the limiting point. So if it goes far enough along a sequence, the Cauchy criterion says that the distance between any two elements in the sequence far enough must be arbitrarily small. So we can pick any small epsilon positive number, and if a sequence is convergent according to the Cauchy criterion, it means that we must be able to find two elements far enough, the distance of which is smaller than this arbitrarily picked epsilon. Okay, so we have the definition of convergence, and we have a very useful criterion, the Cauchy criterion. Actually, we are going to use the Cauchy criterion all along the book because this is the convergence criterion on which the whole book is written. So we will say that the Bellman operator or any other operator we are going to use generates Cauchy sequences of functions. So this is the criterion we are going to use. We have some useful facts, and you can see I'm referring back to exercise 3.5. So this is the reason why I told the other day that exercises and solutions to exercises are so instrumental to completing the book. So what useful facts we have? If we have a sequence and the sequence is converging to x, and the same sequence is converging to y, then x is equal to y. What does it mean? It looks fancy, but what does it mean? It means that if, and this is really important, if a series is convergent, then the limiting point is unique. It is really, really important. So a series cannot converge towards multiple limiting points. If a series is convergent, it has only one limiting point. This is the first useful fact. The second useful fact, Cauchy sequences are bounded. It means that if a sequence is Cauchy, it means that the sequence is convergent, and it means that the sequence cannot go beyond and that cannot go under a certain bound. So they are bounded. Let's go ahead. Let me refer back to the exercises we did at the end of the previous lecture, when we used the Bellman operator to generate a series of functions, value functions, as approximations of the value function of the infinite case. We didn't go into the details, but please trust me, these functions had some, I mean the approximations, these functions had some simple but essential features. They were continuous. They were logarithmic functions, if you remember. So they were continuous, and they were convex. Convexity is just a kind reminder. Convexity is a key feature of utility functions. Convexity means that a utility function expresses the diminishing marginal utility, which is a key ingredient in utility theory. So if we have strictly increasing, strictly concave utility functions, we can say we have the appropriate utility functions. So if we take into account the fact that the value function is the sum of utilities in consecutive, the sum of utilities in consecutive periods, and these utilities in the consecutive periods are measured with the one period utility functions, and if these one period utility functions are strictly concave and strictly increasing, we may expect the value function, the limiting function, the value function of the infinite case to be strictly increasing and strictly concave. Once again, so we defined the value function of the infinite case as the sum of the infinite sum of value functions from the consecutive periods. We measured utility by a simple logarithmic utility function, which is strictly increasing and strictly concave. And we have the reason, so given this, we have the reason to expect the value function of the infinite case to be strictly concave and strictly increasing. So it makes sense. because if the value function describes the utility which the agent can gain from consuming a given initial cake, going back to the cake eating problem, it makes sense to expect the value function to be increasing, because higher cakes give higher utility, higher levels of happiness, and we can expect this value function to be strictly concave, just because the law or rule of diminishing marginal utility. So we need to think about the circumstance whether the repeated use of the Bellman operator really produced a limiting function, the value function of the infinite case, which was appropriate. So whether the repeated use of the Bellman operator gave us a function which was really concave and which was really strictly increasing, strictly concave and strictly increasing. This is not this simple, because it has a lot to do with convergence, and to make sure that we are going to have an appropriate function as the limiting function, we need to make sure that we are moving in a complete space. And this is the key term, a complete space, or complete normed vector space. If we have a complete normed space, vector space, then we can say that any convergence starting in this space or subset of a larger space, so any convergence starting in this space has the limit point, the end point in this space. So more practically, if we start in the space of strictly concave and strictly continuous functions, and if we have an appropriate operator, then the limiting point of our convergence is going to be in the subspace of strictly increasing and strictly concave functions. So all we need is a complete metric space. And if we have a complete metric space, then any Cauchy sequence of functions, and we are going to work with Cauchy sequences, any Cauchy sequence of functions is converging to a point function, a limit function or limiting function in the same space. So on these grounds, we have a very important theorem. This is theorem 3.1. To sum up, the space of bounded continuous functions, this is really instrumental to us. The space of bounded continuous functions is a complete normed vector space. So if we are moving in the space of bounded continuous functions, then we can make sure that any convergence in this space is, any sequence in this space is converging towards a function, towards a point in the same space. So our limiting function is going to be, must be actually, bounded and continuous. Now it's time for us to turn to the second question, how to ensure convergence. Let me go back to the example at the end of the previous lecture. In that exercise, in that lengthy exercise, we were using an operator, we called it the Bellman operator, which was simply the Bellman equation in which we used the outcome of the previous approximation as the value function to have the next approximation to the value function of the infinite case. We saw that this algorithm, this procedure led to the value function as the limiting function of the infinite case, but again we took it for granted. So now it's time for us to look into whether the use of the Bellman operator was justified and how it can be judged whether the use of an operator, for instance the Bellman operator, is justified. We will need to show the following two things, and we will discuss it at length, but without providing the proofs. The proofs are in the book. Please go to the book. So the Bellman operator, the Bellman equation as the operator, generates a Cauchy sequence of value functions. This is the first thing to know, to learn. And the other thing to know and learn, there is a unique limiting point at the end of the convergence process. The concept which we are going to use is contraction mapping. Contraction mapping is a feature of mappings according to which the application of an operator reduces the distance between 2 points. So if you have 2 points, and these points can be points in the Euclidean space, these points can be infinite sequences or functions. If you have 2 points, after applying the operator, a contraction mapping, which is a contraction mapping, after applying an operator, you will have 2 points, but the distance between these resulting points will be smaller than the distance was between the initial points. It is a very useful result. So if we want to ensure that by the use of the Bellman operator leads to the limiting function, the value function, we need to show that the Bellman operator is a contraction mapping theorem. I will get back to this question shortly. So this is the first thing to know. Our most important result is the following. This is theorem 3.2. If we are in a complete metric space, and if we have an operator T, which you can see, this is really important. This mapping maps the space into itself. So it's not questioned anymore that the mapping, if the mapping maps the space into itself, it is proved that the mapping maps the space into itself. So if we have an operator like the Bellman operator, and if we move in a complete metric space, you can see, then it can be taken for granted that the use of the operator leads to a given class of functions. So if we start from continuous and strictly concave functions, by the use of the operator we will have increasing and strictly concave functions. Okay, so the theorem 3.2 says we are in a complete metric space, so the mapping maps the space into itself. So it is a contraction mapping with modulus beta if t has only one fixed point, v, and for any starting point, v0, the repeated application of the operator leads to consecutive approximations to the limiting function, and these limiting functions get to these approximations get closer and closer to the limiting function. So, okay, once again, the contraction mapping is a key concept when it comes to using the Bellman operator, because if the Bellman operator is a contraction mapping, then the application of the Bellman operator or any other operator which is a contraction mapping ensures that by starting from any two initial points in a space, we will have 2 points, but the distance between the resulting 2 points is going to be smaller than the distance between the two initial points. Okay, so interpreting it in the case of the Bellman operator and the value functions, if we start from any initial approximation, then the use initial approximation to the value function, of the infinite case. So if we start out from any arbitrarily chosen initial approximation to the value function of the infinite case, and if we use repeatedly the Bellman operator, we will have further and further approximations to the value function, the limiting function, and if the Bellman operator, if I use the conditional, if the Bellman operator is a contraction mapping, then we can make sure that we get closer and closer to the limiting value function. There is one thing I didn't mention in this slide. I use the conditional. If the Bellman operator is a contraction mapping, then we can make sure that we are converging towards the limiting function. How can we be sure that the Bellman operator is a contraction mapping? This is the point when the so-called Blackwell conditions come into play. I didn't mention it because we don't need to do the exercises. You can read the Blackwell. You can find the Blackwell conditions in the textbook, but let me mention them, the Blackwell conditions. So the Blackwell condition, we have two Blackwell conditions. One is discounting and the other is monotonity. So if we have an operator that, for instance, like the Bellman operator, if we have an operator which abides by these two conditions, then this is a contraction mapping. So luckily, in the case of the Bellman operator, it is quite simple to prove that this is a contraction mapping. It is an easy feat. But if we want to use an operator, the first thing to do is to check these two Blackwell conditions. If they hold, the operator is a contraction mapping, and by the use of the operator, we can get closer and closer to the limiting point. So one result is that the repeated use of the operator takes us closer and closer to the limiting point. And the other result is equally important. There is only one. There is only one fixed point in this sequence. So if we have a contraction mapping, we can make it sure that we are converging to a limiting point, but we can be sure that we have only one limiting point. So if the Bellman operator is a contraction mapping, and if we move in the appropriate, to sum up, if we move in the appropriate space, which is a metric space and which is the space of continuous, strictly increasing and strictly concave functions, we can be certain that the repeated application of the Bellman operator leads us to only one unique value function. So every problem has a unique fixed point in the application of the Bellman operator. Okay, there is a further topic which is covered in chapter 3 of our textbook, and this is the theorem of the maximum. To go back to the cake eating example of the first lecture, just a kind reminder, both the value function and the policy function were continuous. We didn't do anything explicitly to make them continuous. They were continuous, but it is not something we can take for granted. So, but this is a quality which we need. We want the value function and we want the policy function to be continuous. So to ensure it generally, we need further restrictions on the one-period return function and the consecutive approximations, and on the set of the feasible choices which are available at any state. This is a set, so we haven't used so far the feasibility set, this expression, the feasibility set. Going back to the cake eating example, we didn't emphasize that any given state, any given cake size, the agent had a number of options. He or she could eat nothing. He or she could eat all the cake. So this is a closed interval, and there are available options in between the endpoints. So this is an interval. So this is the reason why we say that the correspondence is a set-valued function, because as a function it attaches a closed interval. In fortunate cases, it attaches a closed interval to any given state. Okay, again, this is something we cannot take for granted. So we must pay attention to the correspondence as a set valued function, and we want to make it closed. Another restriction is that the feasible set must be continuous, and this is the point which I want to emphasize. The other restrictions are quite simple and straightforward, so this continuity of the feasibility set is a bit problematic. The authors Lucas and Stokey describe continuity of the feasibility set with two concepts: lower and upper hemi continuity. This figure is very useful. It directly comes from the textbook, and you can see what upper and lower hemi continuity mean. they give the exact definitions, and I don't want to use those definitions. You can read them, so we don't need here. We don't need those definitions. So lower hemi-continuity intuitively means that any inside point, I mean any point inside the feasibility set, has convergent sequences from both directions. And upper hemi-continuity means that every inside convergence has inside limiting point. So on the basis of these definitions, you can see that x1 is lower hemi-continuous but not upper hemi-continuous, and x2 is upper hemi-continuous but not lower hemi-continuous. I think the explanation is simple. Lower hemi-continuity, just to have a look at the details, lower hemi-continuity means that any inside point has a convergent sequence, has convergent sequences from both directions. And if you have a look at point x2, there is a section of the available set under the upper bound to which we cannot converge from the left. So this is the reason why it is not lower hemi-continuous. Okay, instead of trying to describe what it means to have a closed and convex graph as a set graph of the correspondence, let me have an example to show you. This example is a simplified version of the Cass-Koopmans growth model. Okay, so this is our example. The purpose is to find an optimum consumption and actually investment plan that maximizes total utility over an infinite period. So this is the objective function, actually the value function. So we want to maximize the overall utility, which is the value function. Key 0, the initial capital stock is given, and we have an appropriate discount factor. We know that consumption and investment, so next period's capital stock, must be non-negative. We have a transition equation which means that next period capital stock is the sum of current output. A part of next period capital stock comes from capital stock transferred from t to t plus 1, and this is consumption. All right. Okay. We don't have too many variables, so we can say that state at t is the capital stock, and we can say that the control variable is investment. Actually, it's all the same. Trust me, it is simpler to address this problem by having next period's capital stock as the control or decision variable. But if you have a look at the transition equation, you can easily realize that any given k, the state variable, current period t consumption and next period's capital stock are uniquely interrelated. So we have only one decision variable in this model. It can be the capital stock, next period's capital stock. It can be current period consumption, but mathematically it is easier to address the problem if we have next period's capital stock as the control variable. So let's do this. Let's write the Bellman equation of the problem. It's going to look like this. This is the max operator. We have two sequences. One sequence for consumption and one sequence for investment. Utility in the current period and the value function, the same value function as we are on an infinite horizon. Just a minor remark. So in this case, we don't need to and we don't want to approach the value function through through a convergence along the finite cases, because the problem is inherently an infinite problem. So we could do this, but trust me, we can do this directly from the Bellman equation, as we could do the same at the cake-eating example. So we have the Bellman equation. This is the Bellman equation. And we have the transition equation. We can skip the time scripts. So instead of k t plus 1 or ct, we can have this version of the transition equation. The unknown in this problem is the value function itself. So let's have a look at the feasibility constraint, or the set of the feasible choices. How can we get to the graph of this feasibility set? We can assume that there is a closed interval on which the control variable moves. This is a closed interval because this is a closed interval. So there is a lower bound and there is an upper bound, and you can see both bounds are defined by functions. Both functions are functions of k. So this is the way we use the term set valued function. So just a sketch. So if this is the state variable and this is gamma along the horizontal axis, so if we have any k, any value along the horizontal axis, the feasibility constraint, okay, this is lame. The feasibility constraint is an interval. Okay. At another point, we have, this is very schematic, so this is just a sketch. So for any k, we have a closed interval. So it means that the correspondence is a set-valued function. If we do this to all the points along the horizontal axis, we can have something like this. Okay, this is not what we are going to have, it is just an example. So the correspondence is a set-valued function. Okay, so both the lower bound and the upper bound are functions of the state. It means, intuitively, it means that we need an interval to any k, to any state, from which the optimal decisions come. So this is an interval. This is an interval of the feasible choices at any k. All right, let's go on. Given the transition function, we can see, as we claimed a couple of minutes ago, that at any given k, investment, next period's capital stock, directly depends on consumption. So we have the intuition that investment is a function of consumption. So by selecting consumption, actually we make a decision on next period's capital stock. So we need to try to find an interval that contains the feasible set at any k. Evidently, it must be non-negative. So negative investment, negative capital stock is impossible to interpret economically. So the lower bound is 0. Given the dependence, next period's capital stock is the highest when C is 0. So this is the reason why I emphasized the role, the importance of C. So if C, consumption, is 0, we have the maximum amount of next period capital stock. So actually this is the upper bound. This is a function of k, so this is appropriate. The lower bound is 0 and the upper bound is this function. So this is nice. We can say that gamma k is 0, the lower bound is 0, and the upper bound is this function. We are making progress, but it's not the end of the problem. What do we know about the range of the capital stock? So, okay, we clarified an interval for the investment, the control variable, but given the simple fact that this period's choice, next period capital stock, is capital stock next period, so there is a direct connection between the control and the state. So today's control is tomorrow's state. So we want to make sure, we need to make sure that there is no contradiction between the control space and the state space. So between the intervals on which the state variable moves and the control variable moves. So let's go back. I don't need to rewrite. So let's go back to the transition equation. This is a nonlinear difference equation, because next period's capital stock is a function of, okay, I made a mistake. We don't need this form. We focus only on the upper bound. So if we rewrite the upper bound, we can easily realize that this is, as I have just mentioned, this is a nonlinear difference equation. Nonlinear because we didn't specify the production function, which is fk. It may have a steady state in which the capital stock is stable. If there is a steady state, this equality holds. So in the steady state, current period capital stock is the same as next period capital stock, because in the steady state, capital stock is stable. Capital stock is stable. So let's try to solve this equation. It is easy. We can simplify, and in the end we find that delta k is fk upper bar. Delta k upper bar is fk upper bar. So we have a capital stock which is the upper bound, and which is the, so economically this is the highest level of maintainable capital stock. So now we are in a position where we may try to draw the figure of A. So the graph of the feasibility set. So this is the maximum level of maintainable capital stock, and it is easy to realize. There is one thing to realize. So what is the upper bound at the highest level of capital stock? We need to put this k upper bar into the function describing the upper level, and we realize that this is k upper bar. So at k upper bar, the upper bound is k upper bar. So there is a 45-degree line in the middle of the figure, and this is the upper bar. This is mk this is okay. I need to, oh geez, I'm destroying my figure. Okay, this is really nice. So here we go. this is the graph A. So this is the graph of the feasibility set, and this is closed and convex. Closeness comes from the fact that for any state at t, sorry, for any k, we have a closed interval, just like in this, just like in this case. So this graph is closed because it contains all its boundaries. So the white lines are parts of the feasible set, because for any given k, the feasibility set is a closed interval. And so this is closed and this is convex, because if we pick any 2 points inside the set, any convex combinations of these points are still in the set. So instead of trying to explain to you lower hemi-continuity and upper hemi-continuity, I just wanted to show you an appropriate example, what an appropriate, well-behaved, to say so, a well-behaved correspondence looks like.